Deep Sleep Science channel. I'm so glad you've joined me tonight. Tonight, we turn our attention to something so familiar, yet so profoundly mysterious, that humanity has pondered it since the first conscious thought. Time. It flows around us and through us like an invisible river, carrying everything forward in its steady, unstoppable current. We measure it, we feel it, we age within it, yet no one truly understands what it is. Time is both the gentlest and most powerful force in existence. It shapes mountains into sand, transforms stars into light, and turns moments into memories. It connects the Big Bang to this very breath you're taking now. Science has revealed that time is not what we think it is. It bends, it stretches. It may not even flow the way we perceive. Tonight, we'll drift through 100 quiet revelations about time, each one a window into the strange and beautiful nature of existence itself. As we journey together, let these facts wash over you like waves on an endless shore. But for now, there's nothing you need to do. Just let yourself settle. Let your breath slow, and let the quiet vastness of time open like a calm horizon. If you enjoy these gentle journeys, consider liking and subscribing, or share your thoughts in the comments. It helps others find their way here too. Now, if you're ready, let's begin. Time is not a constant. It moves at different speeds depending on where you are in the universe. This revelation, so counterintuitive to our everyday experience, is one of the most beautiful truths that physics has unveiled. We imagine time as a steady metronome, ticking uniformly for everyone and everything, but the universe operates by stranger rules. Time bends and stretches in the presence of gravity, moving faster where gravity is weak, and slowing where gravity pulls with immense force. An astronaut orbiting Earth experiences time differently than someone standing at sea level, though the difference is measured in mere fractions of a second. Yet these fractions accumulate, these tiny distortions compound, revealing that time itself is woven into the very fabric of space, inseparable from it, flexible as water. It is a reminder that reality is far more fluid than our senses suggest, and that the universe holds us all in rhythms we cannot feel, but which shape everything we know. According to Einstein's theory of relativity, time slows down near massive objects like black holes. Imagine standing at the edge of a black hole's influence, where gravity pulls with such ferocious strength that even light cannot escape, and watching a clock on a distant spaceship. From your perspective, that clock would appear to tick more and more slowly, each second stretching into eternity, while for the astronaut holding it, time flows normally. This is not an illusion or a trick of perception, but a fundamental property of the cosmos itself. Gravity warps the dimension of time just as it warps space, creating valleys and peaks in the fabric of reality. Near the event horizon of a black hole, time nearly stops altogether for an outside observer, while the person falling inward experiences time rushing forward. It is as though time is not one river, but countless streams, each flowing at its own pace, all converging in the vast ocean of space-time. A single day on Venus lasts longer than a Venusian year. This strange inversion occurs because Venus rotates on its axis so slowly that it takes 243 Earth days to complete one rotation. Yet it orbits the Sun in only 225 Earth days. In essence, a day on Venus, one sunrise to the next, outlasts the planet's entire journey around its star. The Sun would rise in the west and set in the east, moving with the patience of a glacier. and you would watch an entire year pass before the sun returned to the same position in the sky. It is a world where the rhythms we take for granted dissolve into something alien and dreamlike. Time on Venus moves to a tempo that defies intuition, a reminder that the universe composes its symphony with infinite variations, each world a unique note in the cosmic arrangement. Time as we know it began 13.8 billion years ago with the Big Bang. Before that moment, there was no space, no matter, no energy, and perhaps most strangely, no time. The universe did not exist in a place or at a moment. It simply was not. Then, from a point of infinite density and temperature, everything exploded into being, and with it came the dimension of time, unfurling like a banner in the wind. The first seconds were a blur of unimaginable heat and rapid expansion, particles forming and annihilating in a cosmic dance. But as the universe cooled, time settled into the steady flow we recognize today, carrying matter forward, allowing complexity to emerge, enabling stars to form and galaxies to spiral. Every tick of every clock since that first instant is part of an unbroken chain stretching back to the very beginning, a thread of continuity that connects this quiet moment to the birth of all things. Before the Big Bang, the concept of before may not have existed at all. This is a thought that bends the mind in gentle circles, for how can there be no before? Yet if time itself began with the Big Bang, then asking what came before is like asking what lies north of the North Pole. The question, though natural, may be meaningless. Some theories suggest that time is a property of this universe alone, emerging from quantum fluctuations in ways we are only beginning to understand. Perhaps there are other universes with their own timelines, or perhaps time is cyclical, and our Big Bang was merely one pulse in an eternal rhythm of creation and dissolution. The mystery remains unsolved, a vast unknown that invites wonder rather than certainty. It is a reminder that the deepest questions about existence may not have answers, only deeper layers of awe. Your head ages faster than your feet because of gravitational time dilation. This phenomenon, so subtle that you will never perceive it, is nonetheless real and measurable with atomic clocks. Because your head is farther from the center of the Earth than your feet, it experiences slightly less gravitational pull, and time flows just a fraction faster there. Over the course of a lifetime, your head ages about 90 billionths of a second more than your feet. It is a difference so infinitesimal as to be massive and meaningless in practical terms, yet it reveals something profound, that your body exists in multiple time streams simultaneously, each part experiencing its own tempo, however slightly different. From your neurons to your toes, you are a collection of clocks, all ticking in near-perfect harmony, but never quite synchronized. It is a beautiful reminder that even within yourself, time is not uniform, and that the universe's strangeness extends all the way down to the space between your thoughts and your steps. Astronauts on the International Space Station age slightly slower than people on Earth. As they orbit our planet at speeds of roughly 28,000 kilometers per hour, time dilates according to the principles of relativity, and their clocks tick ever so slightly slower than those on the ground. Over the course of 6 months in space, an astronaut might age about 1/100th of a second less than their earthbound counterparts. They return having traveled, in the most literal sense, into Earth's future, if only by the tiniest margin. It is not the dramatic time travel of science fiction, but it is time travel nonetheless, a consequence of velocity and the malleability of space-time. Each orbit they complete is a small journey through time as much as through space, a reminder that motion itself alters the flow of temporal experience and that the universe treats time as something far more flexible than our everyday lives would suggest. The ancient Egyptians divided day and night into 12 hours each, giving us our 24-hour day. This division was not arbitrary, but born from observation and practicality, rooted in the lunar calendar and the desire to mark time in manageable segments. The Egyptians were among the first to develop sundials and water clocks, devices that allowed them to measure the passage of hours even when the sun had set and the stars wheeled overhead. Their systems spread through trade and conquest, adopted by Greeks and Romans, refined over centuries, until it became the framework by which the entire world now organizes its days. It is remarkable to think that the rhythm of your daily life, the 9-to-5 workday, the midnight hour, the countdown to noon, all trace back to ancient scribes watching shadows lengthen across desert stone. Time, in this sense, is not only a natural phenomenon, but a human construction, shaped by culture and necessity, and passed down like an heirloom through millennia. A single heartbeat of the universe, if the cosmos had a pulse, would last billions of years. Galaxies form, evolve, and sometimes collide over timescales so vast that human lifetimes are less than flickers in comparison. Stars are born from clouds of gas, burn through their nuclear fuel over millions or billions of years, and die in spectacular explosions or slow fade-outs. And this cycle repeats endlessly across the cosmos. If we could speed up time and watch the universe as one might watch a time-lapse film, we would see galaxies breathing, expanding and contracting, swirling in great cosmic dances, pulsing with the rhythm of creation and destruction. But from our vantage point, trapped in the narrow window of a human lifespan, the universe appears almost frozen, unchanging, eternal. It is only when we measure time in eons that we see the heartbeat, slow and steady, each contraction and expansion, a chapter in the universe's long, patient story. The Earth's rotation is gradually slowing down, making days longer over millions of years. The Moon's gravitational pull creates tidal friction, a gentle but persistent drag on Earth's spin, causing our planet to lose a tiny amount of rotational energy with each passing day. The effect is minuscule, about 1.7 milliseconds per century. But over geological time, it accumulates into something significant. 1 billion years ago, a day on Earth lasted only about 18 hours. 1 billion years from now, if Earth and the Moon still exist in their current relationship, days will be even longer still. The Moon itself is slowly drifting away, receding from Earth at a rate of about 3.8 centimeters per year. And as it does, it takes a little bit of Earth's spin with it. It is a cosmic exchange, a slow waltz between two celestial bodies, and a reminder that even the most fundamental rhythms of our existence are not permanent, but are subject to the patient, relentless forces of physics. When dinosaurs walked the Earth, a day was only about 23 hours long. This means that a year in the Mesozoic era contained more days than a year does now, and the Moon hung closer to the horizon, appearing larger and more luminous in the ancient sky. The great sauropods, lifting their necks toward the heavens, watched a moon that exerted stronger tides, creating more dramatic ebbs and flows along primordial coastlines. The Earth spun faster. and the rhythm of life moved to a slightly quicker tempo. Yet the dinosaurs, of course, knew nothing of hours or minutes. They lived by the sun and the seasons, by hunger and instinct, oblivious to the fact that the very rotation of their world was gradually winding down. It is humbling to think that the planet itself changes over time, that the length of a day is not fixed, but is written in the dynamic relationship between Earth and Moon, a relationship that has been evolving since the Moon's violent birth billions of years ago. The Moon is slowly drifting away from Earth, which affects the length of our days. Each year, the Moon moves approximately 3.8 centimeters farther from us, a distance so small as to be imperceptible in a human lifetime, but profound over deep time. This gradual recession is the result of tidal interactions, a transfer of angular momentum from Earth to the Moon, causing Earth's rotation to slow and the Moon to spiral outward in compensation. In the distant past, shortly after the Moon formed from the debris of a colossal impact, it orbited much closer, looming enormous in the sky, and Earth's day lasted only a few hours. Over billions of years, this cosmic dance has stretched our days and pushed the Moon farther into the darkness. Eventually, in the unimaginably distant future, the Moon will stop receding when Earth and Moon become tidally locked, both showing the same face to each other for all eternity. But that day lies so far ahead that the Sun itself may have long since expanded into a red giant. For now, the Moon drifts quietly away, a slow goodbye measured in geological epochs, and we remain unaware, spinning beneath its gentle, fading influence. Light from the Sun takes 8 minutes to reach Earth, meaning we see the Sun as it was in the past. Every sunrise you witness is light that left the Sun's surface 8 minutes and 20 seconds earlier, racing across the void at 300,000 kilometers per second, carrying warmth and energy across the cold expanse of space. When you look up at the Sun, never directly of course, but sensing its presence, feeling its heat, you are not seeing it as it is now, but as it was in the recent past. If the Sun were to suddenly vanish, we would not know for those 8 minutes. The light would still arrive, the sky would still glow, and only after that brief delay would darkness fall. This lag is not unique to the Sun. It is a fundamental property of light and distance, a reminder that observation itself is an act of looking backward through time, and that the present moment, as we experience it, is always a mosaic of different pasts arriving at different speeds. When you look at distant stars, you're seeing them as they were thousands or millions of years ago. The night sky is not a snapshot of the present, but a tapestry of the past. Each point of light a messenger from a different era. The star Sirius, brightest in our night sky, shows itself as it was 8.6 years ago. Betelgeuse, that red giant in the constellation Orion, appears as it was more than 500 years in the past. Some of the faint stars you can barely perceive are so distant that their light has been traveling toward your eyes since before human civilization began, crossing the void while empires rose and fell, while continents shifted and species evolved. It is entirely possible that some of the stars you see no longer exist, having exhausted their fuel and collapsed or exploded. Yet their light continues its journey, a ghostly echo of something long gone. When you gaze upward on a clear night, you are not merely looking out into space but peering backward through time itself, witnessing the universe as it once was, layer upon layer of history written in light. The oldest light in the universe is the cosmic microwave background radiation, a whisper from 380,000 years after the Big Bang. Before this moment, the universe was so hot and dense that photons could not travel freely. They scattered endlessly off charged particles in a glowing fog. But as the universe expanded and cooled, electrons and protons combined to form neutral atoms, and suddenly light could move unimpeded across space. That first free light, released in all directions, has been traveling ever since, stretched and redshifted by the expansion of space itself, until now it reaches us as faint microwave radiation, a gentle glow just a few degrees above absolute zero. This light is everywhere, filling the cosmos uniformly, a relic of the universe's infancy that surrounds us at every moment. When scientists tune their instruments to detect it, they are listening to the oldest signal in existence, a cosmic lullaby that has been humming for nearly 13.8 billion years, carrying information about the birth of everything. It is the most ancient thing we can observe, the farthest we can see into the past. And it tells us that the universe, for all its vastness and violence, began in light. Time passes differently for particles moving at near light speed. In particle accelerators, subatomic particles are accelerated to velocities approaching the speed of light, and as they do, time slows dramatically for them relative to the laboratory. Unstable particles that would normally decay in microseconds live far longer. When moving at these extreme speeds, their internal clocks running slower and slower as their velocity increases. This is not theoretical. It is measured, confirmed, and accounted for in every high-energy physics experiment. The particles experience their normal lifespan, ticking along at their usual rate. But to us, watching from the outside, they seem to persist impossibly long. It is a direct, observable consequence of relativity, a window into the strange truth that time is not absolute but relative, dependent on motion and perspective. These particles, racing through magnetic fields at nearly the speed of light, are time travelers in the most literal sense, aging more slowly than the world around them, living longer than they have any right to, by the standards of their stationary cousins. It is a small miracle, repeated millions of times per second in laboratories around the world, a testament to the universe's deep and beautiful strangeness. Your biological clock is controlled by a tiny cluster of neurons in your brain, called the suprachiasmatic nucleus. Nestled just above the point where your optic nerves cross, this minuscule region contains about 20,000 neurons that coordinate the rhythms of your body with the cycle of day and night. It receives direct input from your eyes, detecting the presence or absence of light, and uses this information to regulate the release of hormones, the rise and fall of body temperature, the ebb and flow of alertness and sleepiness. When morning light enters your eyes, the suprachiasmatic nucleus signals to your pineal gland to stop producing melatonin, the hormone of darkness, and you begin to wake. As evening falls and light fades, the process reverses, and melatonin floods your system, preparing you for sleep. This internal clock runs on a cycle slightly longer than 24 hours, which is why it must be reset each day by exposure to light. It is a remarkable piece of biological engineering, a timekeeper that evolved over millions of years, allowing your ancestors to anticipate the coming of dawn and the falling of night, synchronizing their physiology with the turning of the planet. Without it, you would drift, untethered from the rhythm of the world, lost in a fog of irregular sleep and wakefulness. Humans have an innate sense of time that exists even without external cues. Studies of people isolated in caves or bunkers deprived of sunlight and clocks, reveal that the body maintains its own rhythm, cycling through periods of wakefulness and sleep in roughly 24-hour intervals. This internal sense is not perfectly accurate. It tends to run slightly long, between 24 and 25 hours. But it persists regardless of external information. You can feel time passing even in complete darkness, even in silence. Your brain counts moments, estimates durations, anticipates events. This ability is fundamental to survival, allowing organisms to predict when food will be available, when predators are most active, when it is safe to rest. But it is also imperfect and subjective. Time seems to stretch when you are bored or in pain, and it accelerates when you are absorbed in a task or lost in conversation. Your perception of time is constructed, a model built by your brain from sensory input, memory, and expectation. And like all models, it is an approximation, a best guess at the true nature of temporal flow. Yet even with its imperfections, this sense is one of the most essential features of consciousness, the framework within which all experience unfolds. The circadian rhythm evolved over billions of years, present even in single-celled organisms, long before animals developed brains or nervous systems, before plants reached toward the sun. Even the simplest bacteria possessed internal mechanisms to track the cycle of day and night. Cyanobacteria, which perform photosynthesis, have genes that oscillate on a roughly 24-hour cycle, allowing them to prepare for daylight and maximize energy capture. This ancient clock, refined and elaborated through eons of evolution, has been inherited and adapted by nearly every form of life on Earth. From fungi to fruit flies, from algae to humans, the circadian rhythm is a universal inheritance, a molecular metronome that connects all living things to the rotation of the planet. It is older than eyes, older than leaves, older than the first animals that crawled onto land. It is a rhythm written into the very chemistry of life, a testament to the fact that time is not merely a backdrop against which life unfolds, but an integral part of the structure of biology itself, woven into DNA, expressed in proteins, and manifested in the daily cycles of every cell. Trees mark time in their rings, each circle a year of patient growth. In spring and early summer, when water and nutrients are abundant, trees grow rapidly, producing large, light-colored cells. In late summer and fall, growth slows, and the cells become smaller and darker. This alternation creates the visible rings that tell the story of a tree's life, recording not just years, but conditions. A wide ring indicates a good year with ample water and warmth, while a narrow ring suggests drought or cold. By counting these rings, scientists can determine the age of a tree, and by studying their patterns, they can reconstruct climates of the past, revealing decades or even centuries of environmental history. Some trees, like the ancient bristlecone pines, have lived for thousands of years, and their rings form an archive of time stretching back before the rise of civilizations. Each ring is a chapter, a silent record of a year lived slowly, and together they form a book of time written in wood, a chronicle of seasons that can be read long after the tree has fallen and returned to the earth. The Grand Canyon was carved by the Colorado River over approximately 6 million years. Water, flowing patiently and persistently, cut through layers of rock, grain by grain, millennium by millennium, until it had excavated one of the most breathtaking landscapes on Earth. The process was not dramatic or sudden. It was the slow, steady work of erosion, of water carrying sediment downstream, of freezing and thawing, of gradual deepening and widening. The canyon walls reveal nearly 2 billion years of geological history, layer upon layer of ancient seas, deserts, and rivers, each stratum a page in the Earth's autobiography. To stand at the rim and look down into that immense chasm is to witness time made visible, to see the accumulated effect of 6 million years of patient sculpting. The river still flows at the bottom, still carving, still deepening, and in another 6 million years, the canyon will be different still, though none of us will be here to see it. It is a monument to the power of time, to the way small forces, applied consistently over vast durations, can reshape the very face of the planet. A single second is defined by 9,192,631,770 vibrations of a cesium-133 atom. This extraordinarily precise definition, adopted in 1907, replaced older definitions based on the Earth's rotation, which was found to be too irregular. Cesium atoms, when exposed to a specific frequency of microwave radiation, transition between two energy states with perfect consistency, oscillating like tiny metronomes at the quantum level. By counting these oscillations, scientists can measure time with astonishing accuracy, creating atomic clocks that neither gain nor lose more than a second over millions of years. This definition is not arbitrary. It is rooted in the fundamental properties of matter, in the unchanging laws of quantum mechanics that govern the behavior of atoms. Every clock in the world, from the phone in your pocket to the satellites orbiting overhead, ultimately traces its timekeeping back to these atomic oscillations, to the silent, invisible vibrations of cesium atoms in laboratories around the globe. It is a reminder that time, though it feels like a smooth, continuous flow, is built from discrete moments. From countable ticks at the smallest scales of reality, atomic clocks are so precise they would lose only 1 second every 300 million years. These extraordinary instruments, which form the backbone of modern technology, rely on the quantum properties of atoms to measure time with a precision that borders on the miraculous. GPS satellites, which must account for relativistic time dilation to provide accurate positioning, carry atomic clocks on board. The Internet, with its need for perfectly synchronized data transmission across continents, depends on atomic timekeeping. Even the definition of the meter is now tied to the second, defined as the distance light travels in a specific fraction of a second. These clocks are so sensitive that they can detect the subtle effects of gravity on time. An atomic clock placed just a few centimeters higher will tick measurably faster than one lower down. They have become tools for exploring relativity itself, for testing Einstein's predictions and probing the nature of space-time. In their silent ticking, measured in the oscillations of atoms, we have achieved a mastery over time that would have seemed impossible to previous generations. Yet even this precision is not perfect, and scientists continue to develop even more accurate clocks, pushing toward the limits of what is physically possible. Time zones were created in the 19th century to standardize train schedules. Before this innovation, every town and city kept its own local time, based on the position of the sun, and noon occurred at slightly different moments depending on longitude. This system worked well enough when travel was slow, but the advent of railroads, which could cross vast distances in hours, created chaos. A train schedule published in one city would be meaningless in another, and coordination became a nightmare. In 1884, an international conference established a system of 24 time zones. each 1 hour apart, centered on the Greenwich Meridian in England. This was a radical standardization, imposing a uniform grid onto the natural continuous variation of solar time. It was a human decision, a convention, and yet it transformed the way we experience time. Now, we live by clock time rather than solar time, and we adjust our watches when crossing invisible lines drawn across the Earth. It is a reminder that time, at least as we experience it socially, is partly a construction, a shared agreement that allows us to coordinate our lives across distances, and that the past was stranger and more varied than we often imagine. Before clocks, humans marked time as eternum, time by the sun's position, the moon's phases, and the changing seasons. Life moved to the rhythm of natural cycles, and time was measured in harvests and migrations, in the waxing and waning of the moon, in the journey of the sun from horizon to horizon. There were no minutes or seconds, only the broad divisions of morning, noon, and evening, the quarters of the moon, the turning of the year from planting to harvest. This was not a lack of sophistication, but a different relationship with time, one more attuned to the natural world, more flexible and less abstract. The invention of mechanical clocks in medieval Europe began to change this, introducing the idea of hours of equal length, divorced from the natural variation of daylight across seasons. Gradually, time became something that could be owned, measured, and sold, and the rhythms of human life began to synchronize with the tick of gears and the swing of pendulums, rather than the arc of the sun. Yet even now, buried deep in our biology, we remain creatures of the sun and moon, and our bodies still respond to the ancient cues that governed time for our ancestors, even as we live by the arbitrary divisions of the clock. The longest unit of geological time is the eon, spanning hundreds of millions to billions of years. Geologists divide Earth's history into eons, eras, periods, epochs, and ages, each nested within the other like Russian dolls, creating a hierarchy of time that allows them to speak precisely about events in the distant past. The largest division, the eon, encompasses timescales so vast that entire continents can form, drift, collide, and erode away within a single one. Earth has experienced 4 eons since its formation: the Hadean, when the planet was molten and bombarded by asteroids; the Archean, when the first life appeared; the Proterozoic, when oxygen began to accumulate in the atmosphere; and the Phanerozoic, the current eon, which began 541 million years ago with the sudden diversification of complex life. Each eon is a chapter in the planet's story, a span of time so enormous that it challenges comprehension. To think in eons is to adopt the perspective of the planet itself, to see mountains as temporary wrinkles, oceans as fleeting puddles, and even entire lineages of life as brief experiments in the long unfolding of geological time. We are living in the Phanerozoic eon, which began 541 million years ago. The name means visible life, and it marks the point when complex multicellular organisms became abundant and began leaving clear fossils in the rock record. Before this, life existed for billions of years, but it was mostly microscopic, simple, and difficult to detect. The Phanerozoic opened with the Cambrian explosion, a sudden burst of evolutionary creativity that produced most of the major animal groups we see today, from arthropods to chordates. Since then, life has diversified, suffered mass extinctions, and diversified again, filling every available niche on the planet. This eon has witnessed the rise of fish, the colonization of land by plants and animals, the age of dinosaurs, and the emergence of mammals and birds. Humans appeared only in the very last moments of the Phanerozoic, a species so young that our entire existence is barely a flicker in geological time. Yet here we are, aware of the eon we inhabit, able to look back across its vast span and read the story written in stone, a story that continues to unfold with each passing moment. The concept of a year exists because Earth completes one orbit around the Sun. This journey, which takes 365.25 days, defines the rhythm of seasons, the cycle of planting and harvest, the framework within which human civilizations have organized their calendars and their lives. But a year is not a universal unit. It is specific to our planet, a measure tied to the particular distance and velocity of Earth's orbit. On Mercury, a year lasts only 88 Earth days, while on Neptune, a single orbit takes 165 Earth years. A child born on Neptune would not celebrate their first birthday until they were a senior citizen by Earth's reckoning. The concept of a year, then, is not a fundamental property of time itself, but a consequence of orbital mechanics, a measure that emerges from the gravitational dance between a planet and its star. Yet for us, bound to this particular world, the year has become synonymous with time itself. The turning of the calendar, a marker of growth, change, and the passage of our lives. It is a reminder that our perception of time is shaped by the cosmic circumstances of our existence, by the specific orbit of this small blue world as it wheels endlessly around its star. A cosmic year, one complete rotation of our solar system around the Milky Way, takes about 225 million Earth years. While we orbit the Sun itself, along with all its planets, is orbiting the center of our galaxy, traveling at a speed of roughly 828,000 kilometers per hour through space. This galactic orbit is so vast that it takes the Sun an almost incomprehensible length of time to complete a single circuit. During one cosmic year, the face of Earth changes beyond recognition. Continents shift, mountain ranges rise and erode, entire ecosystems come and go, and life itself transforms through countless iterations of evolution. The last time our solar system was in this position in the galaxy, the Triassic period was just beginning, and the first dinosaurs were emerging. Before that, the previous cosmic year saw the rise and fall of entirely different worlds, of ancient forests and forgotten oceans. We live our lives, build our civilizations, and write our histories within the tiniest fraction of a single galactic orbit. And yet the cosmos continues its patient turning, indifferent to the brief sparks of consciousness that flicker within it. The last time our solar system was in this position in the galaxy, dinosaurs had not yet evolved. It was 225 million years ago, during the Triassic period, when the supercontinent Pangaea was still intact, and the world was dominated by reptiles that were not yet the giants we associate with the Mesozoic. The Earth was unrecognizable compared to today. Different continents, different oceans, different climates, and an entirely different cast of creatures. The stars in the night sky would have been in different positions, and the moon hung closer overhead. Yet the fundamental laws of physics were the same. Gravity pulled with the same strength, time flowed at the same rate, and the Sun orbited the galaxy along the same path. Since that distant era, the solar system has traced its long arc through space, carrying Earth and all its inhabitants on a journey measured not in miles, but in eons. And now, Having completed one full circuit, we find ourselves back where we started, though everything has changed. It is a dizzying thought, a reminder of the scales on which the universe operates and the incomprehensible antiquity of the cosmos. Glaciers move so slowly that their motion is measured in centimeters per day, yet over time they reshape continents. These vast rivers of ice, formed from centuries of accumulated snowfall, creep down mountainsides and across valleys under the immense pressure of their own weight, grinding rock into powder, carving deep U-shaped valleys, and transporting boulders hundreds of kilometers from their origins. A glacier may advance only a few meters per year, a pace so slow as to be invisible to the human eye. But given thousands or millions of years, glaciers become geological forces of immense power. During the ice ages, vast ice sheets covered much of the northern hemisphere, and when they retreated, they left behind a transformed landscape. The Great Lakes, the fjords of Norway, the rolling moraines of the Midwest. Even now, glaciers in Greenland and Antarctica hold enough ice to raise global sea levels by dozens of meters, a reminder that these slow-moving giants still shape the destiny of the planet. Time, when given enough of it, turns even the gentlest forces into world changers, and glaciers are among the most patient sculptors in nature's workshop. The oldest known mineral on Earth, a zircon crystal, is 4.4 billion years old. This tiny grain, smaller than a sand particle, was found in Western Australia, embedded in much younger rock, a survivor from the planet's earliest days. Zircon is extraordinarily durable, resistant to heat, pressure, and chemical weathering, which is why this crystal has endured for so long, even as the rocks around it were melted, reformed, and melted again through countless cycles. By analyzing the isotopes within it, scientists can glimpse the conditions of the early Earth, inferring that liquid water may have existed on the surface far earlier than previously thought, perhaps within a few 100 million years of the planet's formation. This single crystal is a time capsule, a messenger from an era when Earth was still cooling from its violent birth, when the moon was newly formed and hung enormous in the sky, when the first crust was solidifying over an ocean of magma. To hold such a crystal, or even to know of its existence, is to touch deep time, to connect across an abyss of billions of years to the infancy of the world. Radioactive elements decay at perfectly predictable rates, making them nature's clocks. Certain isotopes are unstable and transform into other elements over time, releasing particles and energy in the process. And this decay occurs at a fixed rate that is unaffected by temperature, pressure, or chemical environment. This constancy makes radioactive decay one of the most reliable methods for measuring the age of rocks, fossils, and even the Earth itself. By comparing the ratio of parent isotopes to daughter isotopes in a sample, scientists can calculate how much time has passed since the material formed. It is a clock built into matter itself, ticking away at the atomic level, counting down the eons with unwavering precision. These natural clocks have revealed the age of the Earth, the timing of mass extinctions, the pace of evolutionary change, and the chronology of human history. Without them, we would be adrift in time, unable to place events in their proper sequence. But with them, we can read the deep history of the planet as clearly as reading marks on a ruler. Carbon-14 dating allows us to determine the age of once living things up to about 50,000 years old. This technique exploits the fact that living organisms constantly absorb carbon from the atmosphere, including a small amount of radioactive carbon-14, which is produced by cosmic rays in the upper atmosphere. When an organism dies, it stops taking in carbon, and the carbon-14 it contains begins to decay at a known rate, with a half-life of about 5,030 years. By measuring how much carbon-14 remains in a sample of bone, wood, or fabric, scientists can determine how long ago the organism died. This method has revolutionized archaeology and anthropology, allowing researchers to date ancient artifacts, establish timelines for human migrations, and piece together the story of civilizations long vanished. It is a clock that runs for tens of thousands of years, perfect for the timescales of human history, and it has given us the ability to see into the recent past with remarkable clarity. Every ancient campfire, every buried settlement, every forgotten tool can now be placed in time, connected to the long thread of human experience. The half-life of uranium-238 is 4.5 billion years, nearly as old as Earth itself. This means that if you could gather a kilogram of pure uranium-238 today, half of it would still remain, unchanged, 4.5 billion years from now, assuming the universe itself endures that long. This extraordinary stability makes uranium-238 one of the most useful tools for dating ancient rocks and meteorites, allowing geologists to peer back to the very formation of the solar system. The fact that uranium atoms decay so slowly, at a pace measured in eons rather than years, speaks to the deep structure of nuclear forces, to the delicate balance between attraction and repulsion that holds atomic nuclei together. Some of the uranium in Earth's crust has been decaying since the planet coalesced from the disk of dust and gas surrounding the young sun, and it will continue to decay long after the sun has exhausted its fuel and faded into darkness. It is a clock that began ticking at the birth of the world and will continue until the world's end, a measure of time so vast that even geological eons seem brief in comparison. Coral reefs grow at a rate of just a few millimeters per year, yet create structures visible from space. These living monuments are built by countless tiny polyps, each one no larger than a pinhead, secreting calcium carbonate to form protective skeletons. Generation after generation, the polyps live, reproduce, and die, and their skeletons accumulate layer upon layer, slowly constructing vast underwater cities. The Great Barrier Reef, the largest living structure on Earth, has been growing for approximately 500,000 years, though much of its current form is only about 8,000 years old, having regrown since the last ice age when sea levels were much lower. To stand before a coral reef is to witness the cumulative effect of millions of individual lives, each one brief and fragile, yet together creating something enduring and magnificent. It is a testament to the power of patience, to the way small actions repeated over immense spans of time can build wonders that dwarf any single organism. The reef grows in silence in the warm, clear waters of tropical seas, oblivious to its own grandeur, a monument to the slow, steady creativity of life itself. Stalactites and stalagmites in caves form over thousands of years, one water drop at a time. Each drop that falls from the cave ceiling carries a tiny amount of dissolved calcium carbonate, and when it reaches the air, some of the carbon dioxide escapes, causing a microscopic amount of calcite to precipitate. Drop by drop, year by year, these mineral deposits accumulate, growing downward from the ceiling as stalactites or upward from the floor as stalagmites, eventually meeting to form columns. The process is so slow that it can take centuries for a stalactite to grow a single centimeter. Yet given enough time, tens of thousands or even hundreds of thousands of years. These formations can reach from floor to ceiling, creating the otherworldly landscapes found in caverns around the world. Each layer within them is a record of the past, capturing information about ancient climates, changes in rainfall, and shifts in the chemistry of the surrounding rock. To walk through such a cave is to enter a cathedral of time, where every pillar and curtain of stone is a frozen river of millennia, shaped by nothing more than the patient drip of water in darkness. The concept of now is different for everyone. Your now and mine exist in slightly different moments. Because light travels at a finite speed, and because we are separated by distance, the information about your present moment takes time to reach me, and vice versa. When we stand face to face, this delay is measured in nanoseconds, imperceptible and meaningless, but it is real nonetheless. If you were on Mars and I were on Earth, the delay would be minutes, and the concept of a shared now would become clearly absurd. By the time I saw you wave, you would have moved on to some other action. Even our perception of simultaneity depends on our frame of reference. Events that appear to happen at the same time for one observer may occur in a different order for another observer moving at high speed. This is not a trick of observation, but a fundamental feature of space-time, a consequence of relativity. The present moment, which feels so solid and universal, is actually a subjective construct, unique to each observer. And the idea of a single universal now extending across the cosmos is an illusion born from our limited experience of speed and distance. It takes about 250 million years for our Sun to complete one orbit around the galactic center. This is another measure of the cosmic year, though slightly refined from earlier estimates, and it reminds us that even our Sun, which seems so permanent and central to our existence, is itself in motion, orbiting the supermassive black hole at the heart of the Milky Way, along with hundreds of billions of other stars. The Sun has completed this journey approximately 20 times since its formation, and it will complete it perhaps another 20 times before it exhausts its hydrogen fuel and begins to die. Each orbit takes the Sun and its retinue of planets through different regions of the galaxy, sometimes passing through the spiral arms where star formation is active, and supernovae are more common, sometimes drifting through quieter regions between the arms. Some scientists speculate that these passages may influence conditions on Earth, perhaps affecting climate or even the rate of mass extinctions, though the evidence remains debated. Regardless, the fact remains that we are passengers on a star that is itself a passenger on a much grander journey, a journey measured not in years or centuries, but in the slow wheeling of the galaxy itself. Time dilation means astronauts returning from space have technically traveled into Earth's future. This is not science fiction, but established fact, confirmed by precise atomic clocks flown on spacecraft and shuttles. When astronauts return from months aboard the International Space Station, they have aged fractionally less than people who remained on Earth, their time having moved slightly slower due to their velocity and their position in a weaker gravitational field. The difference is tiny, mere milliseconds over the course of a mission, but it is measurable and real. They have, in effect, skipped forward through time, arriving at a moment that is slightly ahead of where they would have been had they remained stationary. For long journeys into deep space, at higher velocities or near more massive objects, the effect would be far more pronounced. A traveler approaching the speed of light could return to Earth decades or centuries after departure, having aged only a few years. Time travel into the future is not only possible, it happens every time something moves, though usually on scales too small to notice. It is woven into the fabric of motion itself, an inescapable consequence of the universe's relativistic nature. The arrow of time, why time flows forward, remains one of physics' deepest mysteries. The laws of physics, at their most fundamental level, are time reversible, meaning that the equations governing particles and forces work equally well, whether time moves forward or backward. If you filmed a collision between two particles and played it in reverse, the reversed version would obey the same physical laws as the original. Yet our experience of time is profoundly directional. Eggs break, but do not spontaneously reassemble. Memories form of the past, but not the future. And we age inexorably from birth toward death. Something breaks the symmetry. Something gives time its arrow, its sense of forward motion. And that something appears to be entropy. The universe began in a state of extraordinarily low entropy, highly ordered and concentrated, and has been gradually spreading out, becoming more disordered ever since. This increase in entropy, this slide toward equilibrium, gives time its direction, its sense of before and after. Without it, time might have no arrow at all, and the universe would be a static, unchanging landscape where past and future were indistinguishable. It is one of the great unsolved questions, a puzzle that sits at the intersection of thermodynamics, cosmology, and philosophy. Entropy, the gradual decline into disorder, gives time its direction. This concept, born from the study of heat engines and thermodynamics, has become one of the most profound principles in all of science. Entropy measures the number of ways a system can be arranged at the microscopic level while still appearing the same at the macroscopic level. And the second law of thermodynamics states that entropy always increases, or at best remains constant, in an isolated system. A broken glass has higher entropy than an intact one, because there are far more ways for the fragments to be scattered than for them to be arranged into a perfect sphere. A mixed cup of coffee and cream has higher entropy than two separate liquids. The universe, in its entirety, is marching toward a state of maximum entropy, a condition called heat death, where all energy is evenly distributed and no work can be done. This inexorable increase is what gives time its arrow. It is why we remember the past and not the future, why cause precedes effect, why things fall apart rather than spontaneously assemble. Yet locally, in pockets of space sustained by energy flow, entropy can decrease. Life itself is a temporary reversal of entropy, creating order and complexity at the expense of increasing disorder elsewhere. We are islands of decreasing entropy in a sea that is slowly, inevitably, becoming uniform and still. At the quantum level, many processes are time reversible, making the arrow of time even more mysterious. Quantum mechanics, the theory that governs the behavior of particles at the smallest scales, contains equations that are symmetric with respect to time. An electron moving forward through time and an electron moving backward through time are mathematically equivalent in most quantum processes. This symmetry at the fundamental level makes the emergence of irreversibility and the arrow of time at larger scales all the more puzzling. How does a universe built from time-reversible components give rise to irreversible phenomena like aging, decay, and the one-way flow of causation? The answer likely involves the measurement process, the interaction between quantum systems and their environments, and the role of entropy in collapsing quantum superpositions into definite outcomes. But the full picture remains elusive, a gap between the microscopic and macroscopic worlds that physicists are still working to bridge. It is a reminder that the universe operates by different rules at different scales, and that time itself may be an emergent property, something that arises from deeper, more fundamental processes that we are only beginning to understand. Your brain constructs your sense of time, making it feel faster when you're engaged and slower when you're bored. Time is not experienced passively. It is actively assembled by your nervous system from a stream of sensory input, memory, and expectation. When you are absorbed in a task, your brain processes information efficiently, and fewer new memories are formed. So in retrospect, time seems to have passed quickly. When you are bored or anxious, your brain is hyper-aware, processing every moment in detail, and time feels like it drags on endlessly. This is why a watched pot never boils, why a thrilling vacation seems to fly by but feels long in memory, why childhood summers seemed endless, but adult years vanish in a blink. Your perception of time is malleable, shaped by attention, emotion, and the novelty of experience. It is not an objective measure, but a psychological construction. And like all constructions, it is subject to distortion and illusion. The clock on the wall ticks steadily, indifferent, but the clock in your mind speeds and slows, stretches and compresses, dancing to rhythms only you can feel. Time appears to speed up as we age, because each year becomes a smaller fraction of our total lived experience. When you are 10 years old, a single year represents 10% of your entire life, a significant chunk of time. When you are 50, a year is only 2%, and it feels proportionately briefer. This proportional theory, though not the only explanation, captures something true about the subjective experience of aging. As we grow older, we also encounter fewer novel experiences. Life becomes more routine, and the brain encodes fewer distinct memories, which makes time seem to pass more quickly in retrospect. Childhood is filled with firsts: first day of school, first friend, first heartbreak, and each of these moments is etched vividly into memory, making those years feel expansive. Adulthood, by contrast, often settles into patterns, and weeks blend into months, months into years, until suddenly decades have passed and we wonder where the time went. It is a bittersweet aspect of being human, this acceleration of subjective time, a reminder to savor moments, to seek novelty, to remain present, because the river of time flows faster the farther downstream we drift. Children perceive time more slowly because they're processing more new information. Every experience in childhood is fresh, unfamiliar, demanding the brain's full attention and creating rich, detailed memories. A child's day is filled with learning, how to tie shoes, how to read, how to navigate social dynamics. And this constant processing makes time feel dilated, stretched out, almost infinite. A summer vacation in childhood could feel like an eternity, each day packed with discovery and play. As we age and gain experience, the brain becomes more efficient, recognizing patterns and making predictions, and it no longer needs to encode every detail. This efficiency is useful for navigating the world, but it comes at a cost. Time begins to feel like it moves more quickly, and days blur together. The vividness of childhood memory, the sense that those years lasted forever, is a direct consequence of the brain's heightened state of learning. It is a reminder that time is not just something that happens to us, but something we experience through the lens of consciousness, and that lens changes as we grow. The ancient Greeks had two concepts of time: chronos, chronological time, and kairos, the right or opportune moment. Chronos is the time we measure with clocks, the steady quantitative march of seconds and minutes, the time that fills our calendars and regulates our schedules. It is impersonal, relentless, and indifferent to human affairs. Kairos, by contrast, is qualitative, a fleeting window of opportunity, the perfect moment to act, to speak, to create. It is the artist recognizing when a work is finished, the athlete sensing the exact instant to make a move, the lover knowing when to say the words that will change everything. Kairos cannot be measured or predicted. It can only be recognized and seized. The Greeks understood that life is lived not just in the horizontal flow of chronos, but in the vertical depths of kairos, in those rare moments when time seems to open up and reveal its hidden richness. Modern life, dominated by schedules and deadlines, often forgets kairos, reducing all time to chronos. But the distinction remains important, a reminder that not all moments are equal, and that some instants carry a weight and significance that transcends mere duration. Redwood trees can live for more than 2,000 years, witnessing centuries pass in patient silence. These towering giants, some reaching heights of over 100 meters, grow slowly in the coastal fog of California, their roots intertwined with those of their neighbors, creating interconnected networks that share water and nutrients. A tree that germinated during the Roman Empire might still stand today, having survived fires, droughts, storms, and the rise and fall of countless human generations. Its rings record the history of the climate, each one a year of growth, and within its wood is encoded a chronicle of environmental change stretching back millennia. To walk among redwoods is to enter a realm where human timescales feel insignificant, where the lifespan of a single organism dwarfs the span of civilizations. These trees are not hurried. They have no need to be. They simply grow year after year, century after century, accumulating mass and height with a patience that borders on the eternal. They remind us that time can be experienced in many ways, and that longevity itself is a form of wisdom, a testament to resilience and adaptability. The oldest known living organism is a Great Basin bristlecone pine tree, over 5,000 years old. This gnarled, twisted tree, clinging to a harsh mountainside in California, was already ancient when the pyramids of Egypt were being built. It has weathered more than 5 millennia of storms, droughts, and temperature fluctuations, growing so slowly that its wood is extraordinarily dense, resistant to rot and insects. Named Methuselah, though its exact location is kept secret to protect it from vandalism, this tree has been alive longer than any written language has existed, longer than any continuous human civilization. It is a direct, living connection to the deep past, a witness to the entire span of recorded history and beyond. Its roots draw water from the same soil they have touched for 5,000 years, and its needles photosynthesize under the same sun that shone on ancient peoples who knew nothing of the modern world. To know that such a tree exists, still alive, still growing, is to feel a profound sense of continuity, a reminder that life, when given the right conditions, can persist across timescales that stretch the limits of imagination. Tardigrades can enter a state of suspended animation, effectively pausing their personal time for decades. These microscopic creatures, also known as water bears, are among the most resilient organisms on Earth. When conditions become unfavorable, when water dries up, when temperatures plummet or soar, when radiation levels spike, tardigrades curl up into a desiccated form called a ton, expelling nearly all the water from their bodies and entering a state called cryptobiosis. In this state, their metabolism drops to undetectable levels, and they can survive for years, even decades, completely inert. When water returns, they rehydrate and resume normal activity within hours, as if no time had passed at all. They have survived the vacuum of space, extreme pressures, and doses of radiation that would be lethal to most life. From their perspective, time spent in cryptobiosis does not exist. They simply skip over it, pausing the clock of their lives until conditions improve. It is a form of time travel, a way of waiting out unfavorable circumstances by stepping outside the normal flow of biological time. And it speaks to the extraordinary adaptability of life, its ability to find ways to endure even in the face of the most hostile environments. Some species of jellyfish are biologically immortal, theoretically resetting their biological clocks indefinitely. The Turritopsis dohrnii, a small jellyfish found in warm ocean waters, possesses a remarkable ability. When injured, starving, or aging, it can revert to its juvenile polyp stage, effectively restarting its life cycle. This process, called transdifferentiation, allows its cells to transform from one type to another, and the jellyfish can repeat this cycle indefinitely, never dying of old age. In theory, barring predation, disease, or environmental catastrophe, a Turritopsis could live forever, cycling through maturity and youth in an endless loop. It is not immortal in the sense of being indestructible, but it has escaped the biological imperative of aging, the gradual decline that claims nearly every other organism. This discovery has profound implications for our understanding of aging and cellular processes, suggesting that senescence is not inevitable, but is a program that can, under certain circumstances, be reversed. For the jellyfish, time is not a one-way street, but a circle. And death is not a destination, but a point on a loop that can be traversed again and again. Greenland sharks can live for over 400 years, making them the longest-lived vertebrates. These slow-moving predators, which inhabit the cold, dark waters of the North Atlantic and Arctic, grow at a rate of only about a centimeter per year and do not reach sexual maturity until they are well over a century old. The oldest known individual, a female, was estimated to be at least 392 years old, meaning she was born during the reign of James I of England, long before the Industrial Revolution, before the founding of the United States, in a world utterly different from our own. She swam through centuries of human history, oblivious to wars and revolutions, to the rise of technology and the transformation of the planet. Greenland sharks live in cold, deep waters, where metabolic rates are low, which may contribute to their extraordinary longevity. They remind us that the pace of life varies enormously across species, and that time, as experienced by different organisms, unfolds at vastly different speeds. For a creature that may live 4 centuries, a human lifetime is brief, a flicker, and the rapid changes we impose on the ocean are, from the shark's perspective, a sudden, catastrophic disruption. The process of fossilization takes millions of years, turning bone into stone molecule by molecule. When an animal dies and its body is buried in sediment, the soft tissues decay quickly, consumed by bacteria and scavengers. But the bones, teeth, and shells can remain. Over time, as layer upon layer of sediment accumulates above them, the pressure increases and water percolates through the porous bone, carrying dissolved minerals, silica, calcite, iron, which gradually replace the original organic material. This replacement happens atom by atom, preserving the structure in exquisite detail while transforming the composition entirely. What was once living tissue becomes stone, a mineral replica of the original, and this process unfolds over millions of years, so slowly that no human could ever witness it in progress. The fossils we find are not the animals themselves, but echoes, stone memories of creatures that once moved and breathed, now frozen forever in the rock record. They are time travelers, messages from the distant past, and they tell us that the earth remembers, that nothing truly vanishes, that even the most fragile bones can become eternal if given enough time to turn to stone. Continental drift moves at about the same rate your fingernails grow, a few centimeters per year. The continents, those vast masses of rock that seem so solid and immovable beneath our feet, are in fact drifting slowly across the surface of the planet, carried by convection currents in the semi-molten mantle below. The Atlantic Ocean widens by a few centimeters each year as North America and Europe drift apart, while the Pacific shrinks as its floor is subducted beneath surrounding continents. Over millions of years, these tiny increments accumulate into journeys of thousands of kilometers, reshaping the map of the world entirely. 200 million years ago, all the continents were joined into a single supercontinent called Pangaea, and they have been drifting apart ever since, opening new oceans and closing old ones. In the future, they will converge again, forming a new supercontinent, and the cycle will continue. This slow, inexorable motion is invisible in a human lifetime, but it is the engine that builds mountain ranges, triggers earthquakes, and determines climates. It is a reminder that the Earth is not a static stage, but a dynamic, living planet, constantly reshaping itself, and that even the continents are temporary arrangements, drifting passengers on a restless sea of rock. The Himalayan mountains are still growing, rising about 5 millimeters each year. These towering peaks, home to Mount Everest and countless other giants, are the result of an ongoing collision between the Indian and Eurasian tectonic plates. A slow-motion crash that began roughly 50 million years ago and continues to this day. As India pushes northward, the edge of the Eurasian plate crumples and folds, thrusting rock upward into the sky, and the mountains rise millimeter by millimeter, year after year. Erosion works constantly to wear them down. Rivers carve deep valleys, glaciers grind away at the peaks, but the tectonic forces beneath push upward faster than erosion can tear them down, and so the mountains grow taller. In another 10 million years, if the collision continues, they may be even higher than they are now. And Everest, already the tallest mountain on Earth, may rise still farther into the thin, cold air. This is geology in action, the patient, unstoppable force of plate tectonics shaping the world. And it reminds us that even mountains, which seem the very definition of permanence, are transient features, young in geological terms and still actively forming. Glacial ice in Antarctica contains air bubbles that trapped atmosphere from 800,000 years ago. As snow falls and accumulates, it gradually compresses into ice, and tiny pockets of air become sealed within it, preserving a sample of the ancient atmosphere. By drilling deep into the ice sheets and extracting cores, scientists can analyze these bubbles and measure the composition of the air from hundreds of thousands of years in the past. They can determine the levels of carbon dioxide, methane, and other gases, and reconstruct past climates with remarkable precision. The ice acts as a time capsule, a frozen archive that records not just temperature and precipitation, but the very breath of the ancient world. Some of the ice at the base of the Antarctic ice sheet has been there for nearly 1 million years, compressed under the weight of everything above it. And within those depths are secrets about climate cycles, volcanic eruptions, and changes in the Earth's orbit. To hold a piece of this ice, to see the bubbles trapped within, is to hold a fragment of deep time, a tangible connection to an Earth that existed long before humans walked upon it. The light from the Andromeda galaxy takes 2.5 million years to reach your eyes. When you look up on a dark night and spot that faint, fuzzy patch in the constellation Andromeda, you are not seeing it as it is now, but as it was in the distant past, when our ancestors were just beginning to walk upright on the African plains. The photons entering your eyes have been traveling through the void for all that time, crossing the immense gulf of intergalactic space at the speed of light. And they arrive now, in this moment, to tell you a story about a galaxy that has changed, evolved, and moved on in the millennia since they departed. Andromeda is our nearest large galactic neighbor, and it is hurtling toward us at a speed of about 110 kilometers per second. In 4 billion years, it will collide with the Milky Way, and the two galaxies will merge into a single, larger galaxy. But tonight, you see it as it was long ago, a reminder that the universe is vast beyond comprehension, and that looking out into space is always, inevitably, looking back through time. If you could travel at light speed, time would stop entirely from your perspective. This is one of the most counterintuitive predictions of Einstein's theory of relativity, yet it follows directly from the mathematics. As your velocity approaches the speed of light, time dilation becomes more and more extreme, and at exactly the speed of light, time ceases to flow at all for you. From the perspective of a photon racing through space, no time passes between the moment it is emitted from a star and the moment it strikes your retina. The journey, which takes years or centuries from our perspective, is instantaneous from its own. Light does not experience time. It exists in a perpetual now, a timeless state that is utterly alien to our experience. This is why nothing with mass can reach light speed. It would require infinite energy, and time would have to stop. But for light itself, for photons that have no mass, this is the natural state of existence. It is a glimpse into the deep strangeness of the universe, where time is not a universal constant, but a variable that depends entirely on motion and perspective. Near a black hole's event horizon, time slows to nearly a standstill for a distant observer. If you could watch someone fall toward a black hole from a safe distance, you would see them moving slower and slower as they approach the point of no return, their clock ticking more and more sluggishly until they appeared to freeze at the edge, never quite crossing over. From their perspective, however, they would fall through normally, experiencing time at its usual pace, utterly unaware that to the outside universe they had become a frozen image stretched across the boundary of space-time. It is the ultimate expression of relativity's strangeness, where time becomes so warped by gravity that observers in different locations cannot agree on when events occur, or even on whether they have occurred at all. Gravitational waves are ripples in space-time itself, caused by massive cosmic events. When black holes spiral into each other and merge, or when neutron stars collide, they send shudders through the fabric of the universe. Distortions in space-time that travel outward at the speed of light, like ripples on a pond. These waves were predicted by Einstein over a century ago, but they were not detected until 2015, when instruments sensitive enough to measure a distortion smaller than the width of a proton finally captured their passage through Earth. The waves carry information about the events that created them, allowing us to witness cosmic violence that occurred billions of years ago and billions of light years away. To detect a gravitational wave is to feel time and space themselves trembling, to know that the universe is not a static stage, but a dynamic, flexible medium that bends and ripples with the motion of massive objects. The life cycle of a star can span from millions to trillions of years. The most massive stars burn furiously and die young, exhausting their nuclear fuel in only a few million years before exploding as supernovae. Stars like our Sun are more moderate, with lifespans of about 10 billion years, and they die more gently, puffing off their outer layers and leaving behind white dwarfs. The smallest red dwarfs are misers with their fuel, burning so slowly that they can shine for trillions of years, longer than the current age of the universe many times over. Each star is a clock, its lifetime determined by the balance between gravity pulling inward and nuclear fusion pushing outward, and together they populate the galaxy with timepieces of every tempo, from frantic to glacial. A white dwarf star cools down over billions of years, eventually becoming a cold, dark cinder. These stellar remnants, the cores of stars like the Sun that have shed their outer layers, are no longer generating energy through fusion, but simply radiating away their stored heat into space. They begin their existence glowing white-hot, as bright as a living star, but over time they fade through yellow, orange, red, and eventually into darkness. The universe is not yet old enough for any white dwarf to have cooled completely into a black dwarf, but in the unimaginably distant future, when the last stars have died and the cosmos grows dark, these cold embers will drift silently through space, monuments to stars that once burned bright. Neutron stars rotate hundreds of times per second, packing immense time into tiny moments. These incredibly dense objects, formed when massive stars collapse, can spin at rates that seem impossible, completing rotations in milliseconds. Some pulsars, which are rapidly rotating neutron stars that emit beams of radiation, flash hundreds of times per second with a regularity that rivals atomic clocks. The speed comes from the conservation of angular momentum. As the star collapses, it spins faster and faster, just as a figure skater spins faster when pulling their arms in. A neutron star the size of a city can contain more mass than the Sun, and it spins so rapidly that its surface moves at a significant fraction of the speed of light, creating conditions of extreme physics where time, gravity, and motion intertwine in ways that challenge our understanding. The cosmic calendar compresses all 13.8 billion years of history into a single year. Humans appear in the last few minutes of December 31st. In this popular thought experiment, the Big Bang occurs at the stroke of midnight on January 1st, and the present moment arrives at midnight on December 31st. The Milky Way forms in May, the Sun and Earth in September, and the first life appears in that same month. Dinosaurs roam the Earth on Christmas Day and go extinct on December 30th. All of recorded human history, the rise of civilizations, the invention of writing, the building of pyramids and cathedrals, The entire span of art, war, and science fits into the final minute before midnight. It is a humbling visualization, a reminder of how brief our presence has been on this ancient planet, and how much came before us. Tides are caused by the moon's gravity, creating a rhythm that has pulsed for billions of years. Twice each day, the ocean rises and falls, pulled by the gravitational tug of the moon and, to a lesser extent, the sun. This ancient rhythm shaped coastal ecosystems, governed the lives of countless species, and guided human navigation and culture for millennia. The tides have been rising and falling since the moon formed, though they were far more dramatic in the early Earth when the moon hung much closer. They will continue long into the future, gradually weakening as the moon drifts away, a cosmic metronome that beats in synchrony with the celestial dance above. Your body has multiple biological clocks, each keeping time for different organs and systems. Your liver has its own rhythm, optimized for metabolizing nutrients at certain times of day. Your kidneys, your heart, your digestive system all maintain their own schedules, coordinated but distinct. These peripheral clocks are synchronized by the master clock in your brain, but they can also respond to local cues like food intake. This network of timekeepers ensures that your body's processes occur in harmony, that enzymes are produced when needed, that hormones peak and ebb at the right times. It is a symphony of temporal coordination, and when it falls out of sync, health can suffer in subtle but profound ways. Jet lag occurs when your internal clock is out of sync with external time. When you fly across multiple time zones, your body arrives in a new location, but your suprachiasmatic nucleus still believes it is operating on the old schedule. Your hormones, body temperature, and sleep-wake cycle all remain tuned to the time you left behind, and it takes days for them to adjust to the new rhythm of light and dark. This disorientation is a reminder that time, as experienced by the body, is not instantly flexible, but is anchored to cycles that evolved over millions of years, and that our modern ability to cross continents in hours has outpaced our biology's ability to adapt. The master clock in your brain can be reset by exposure to light. The suprachiasmatic nucleus receives direct input from specialized cells in your retina that detect the presence or absence of light, and this information is used to synchronize your internal rhythms with the external day. Bright light in the morning advances your clock, helping you wake earlier, while light in the evening delays it, pushing your sleep time later. This is why exposure to screens at night can disrupt sleep. The blue wavelengths mimic daylight and signal to your brain that it is still day, suppressing melatonin and keeping you alert. Light is the most powerful time cue your body knows, the hand that sets your internal clock each day. Some deep-sea creatures live in eternal darkness and have no concept of day or night. In the abyssal depths where sunlight never penetrates, organisms have evolved without circadian rhythms tied to the solar cycle. They experience time differently, responding instead to other cues like tides, migrations of prey, or internal metabolic cycles. For them, the 24-hour day is meaningless, and time is marked by entirely different rhythms, reminders that the experience of time is not universal, but is shaped by environment and evolutionary history. Cave-dwelling organisms lose their circadian rhythms over evolutionary time. Species that spend generations in lightless caves often evolve to lose their sensitivity to day-night cycles, their internal clocks degrading or disappearing entirely, because they confer no advantage in perpetual darkness. What was once essential becomes vestigial, and time, as measured by the sun, ceases to have meaning. These creatures are living proof that our sense of time is not hardwired into existence, but is an adaptation, useful in some contexts and irrelevant in others. Seasons exist because Earth's axis is tilted at 23.5 degrees. As our planet orbits the Sun, this tilt means that different hemispheres receive varying amounts of sunlight throughout the year. When the northern hemisphere is tilted toward the Sun, it experiences summer, while the southern hemisphere endures winter, and 6 months later, the situation reverses. Without this tilt, there would be no seasons, no spring blooms or autumn harvests, only an eternal sameness. The tilt is a consequence of ancient collisions during the solar system's formation, and it has shaped the rhythm of life on Earth, determining migration patterns, breeding cycles, and the agricultural calendars that gave rise to civilization. The precession of the equinoxes is a 26,000-year cycle caused by Earth's wobble. Like a spinning top that wobbles as it slows, Earth's axis traces a slow circle through space, completing one full rotation approximately every 26,000 years. This wobble causes the position of the stars to shift gradually over millennia, so that the North Star today will not be the North Star in 13,000 years. Ancient astronomers noticed these shifts and recorded them, though they could not explain them. It is a reminder that even Earth's orientation in space is not fixed, but changes over deep time, adding yet another layer of complexity to the measurement of time. Stonehenge was built to mark the passage of time and the changing of seasons. This ancient monument, erected over 4,000 years ago, aligns with the solstices, the moments when the sun reaches its highest or lowest point in the sky. On the summer solstice, the sun rises directly over the Heelstone, and on the winter solstice, it sets between the great trilithons. These alignments suggest that Stonehenge was a calendar, a way of tracking the solar year and predicting the return of the seasons. It is a testament to humanity's ancient obsession with time, our need to mark its passage and find patterns in the celestial rhythms. Ancient humans tracked lunar cycles before they tracked solar years. The moon's phases are immediate and obvious, repeating every 29.5 days, and many early calendars were lunar, dividing the year into 12 or 13 lunar months. The oldest known calendar, carved into a bone over 20,000 years ago, appears to track lunar phases. Only later, with the development of agriculture, did solar calendars become more important, because planting and harvest depend on the sun's annual journey, not the moon's monthly cycle. Both systems persist today, intertwined in complex ways in cultures around the world. A blue moon is simply the second full moon in a calendar month, a quirk of human timekeeping. Because lunar months are slightly shorter than calendar months, occasionally 2 full moons occur within a single month, and the second is dubbed a blue moon. The term has nothing to do with the moon's color. It is purely an artifact of the way we have chosen to organize time. It is a reminder that many of the temporal categories we take for granted are human inventions, imposed on the continuous flow of celestial cycles. Leap years exist because Earth's orbit takes 365 days, not exactly 365. To keep our calendar aligned with the seasons, we add an extra day every 4 years, compensating for the quarter-day discrepancy. Without leap years, the calendar would gradually drift, and eventually winter would arrive in July. The system is not perfect, Leap years are skipped in century years, unless divisible by 400. But it is close enough to keep our timekeeping synchronized with the planet's motion for thousands of years. A nanosecond is 1/1000th of a second. Light travels about 30 centimeters in that time. This infinitesimal duration is the timescale on which computers operate, where billions of calculations occur each second, where electrons race through circuits at speeds approaching that of light itself. In a nanosecond, light moves roughly the length of a ruler, and in the world of high-speed electronics, even this tiny distance matters. It is a measure of time so brief that human perception cannot grasp it. Yet it is the heartbeat of modern technology, the rhythm that underlies every digital interaction. The Planck time is the smallest measurable unit of time, about 10 to 43 seconds. Below this scale, the concepts of space and time, as we know them, break down entirely, and the smooth fabric of space-time dissolves into quantum foam. A seething chaos where the normal laws of physics no longer apply. The Planck time is not just small, it represents a fundamental limit, a boundary beyond which our current theories cannot reach. It is the quantum of time itself, the smallest possible tick of the cosmic clock, and it reminds us that reality, at its deepest levels, is granular rather than continuous. At the quantum level, particles can exist in multiple time states simultaneously. Quantum superposition allows particles to occupy many states at once until they are observed, and this extends even to temporal properties. A particle's history can be uncertain, its past existing in a blur of possibilities that only resolves when measured. This strange behavior challenges our intuition about cause and effect, about the linear flow of time, and suggests that at the smallest scales, the universe operates by rules utterly alien to everyday experience. The theory of quantum mechanics suggests that all possible pasts and futures exist in superposition. In some interpretations, every quantum event causes the universe to branch into multiple versions, each one representing a different outcome, and all of these branches are equally real. If this is true, then time is not a single thread, but an ever-expanding tree of possibilities, and every moment splits into countless futures. It is a dizzying concept, one that transforms time from a river into an infinite maze of branching paths. Some scientists believe time may be an illusion created by quantum entanglement. According to this radical idea, what we perceive as the flow of time might emerge from the relationships between entangled particles, from the correlations that link distant parts of the universe. Time, in this view, is not fundamental, but is constructed, a phenomenon that arises from deeper quantum structures. The theory is speculative, but it represents a profound shift in thinking, suggesting that time itself might be a secondary property of reality rather than a primary one. The universe is approximately 13.8 billion years old, but it will continue for trillions of years to come. The age we often cite is merely the time since the Big Bang, the beginning of this current chapter. But the universe's story is far from over. Stars will continue to form and die for trillions of years. Galaxies will merge and evolve, and new structures will emerge. We exist in what might be called the universe's youth, a time when stars are abundant and energy flows freely. But this era will eventually pass into something quieter and darker. In the far future, stars will burn out, and the universe may enter an era called the heat death. As entropy increases and energy disperses, the universe will cool, star formation will cease, and eventually even black holes will evaporate through Hawking radiation. What remains will be a vast, cold expanse where nothing changes, where time loses its meaning because there are no processes left to mark its passage. It is the ultimate destiny predicted by thermodynamics, a far future so distant that our current universe, with all its stars and galaxies, represents only the briefest flash of light before an eternity of darkness. Time crystals are a newly discovered state of matter that repeat in time rather than space. Ordinary crystals have structures that repeat in space, atoms arranged in regular patterns. But time crystals exhibit patterns that repeat in time, oscillating between states without consuming energy. They represent a new phase of matter, one that challenges our understanding of equilibrium and entropy. Their discovery is recent, their properties still being explored, and they hint at deeper structures in the relationship between time and physical law. Your cells have their own clocks, determining when genes are turned on and off. These cellular clocks regulate everything from DNA repair to metabolism, ensuring that biological processes happen at the optimal times. They tick independently, but are coordinated by signals from the body's master clock, creating a hierarchy of timekeeping that extends from the brain down to individual cells. This temporal organization is essential for health, and disruptions to it are linked to aging, disease, and metabolic disorders. Disrupting your body's natural rhythms can affect everything from mood to metabolism. Shift work, irregular sleep schedules, and constant exposure to artificial light can desynchronize your internal clocks, leading to increased risk of obesity, diabetes, cardiovascular disease, and depression. Your body evolved to function in sync with the day-night cycle, and when that synchrony is lost, systems begin to malfunction. Time, for the body, is not just a measure, but an organizing principle, and respecting it is essential for well-being. Sleep follows a predictable cycle that repeats roughly every 90 minutes. You drift from light sleep into deeper stages, then back up into REM sleep where dreams occur, and this cycle repeats 4 to 6 times each night. Each stage serves different functions: memory consolidation, tissue repair, emotional processing, and together they form the architecture of healthy sleep. This rhythm is ancient, conserved across mammals, a pattern written into the structure of consciousness itself. Deep sleep typically occurs in the first half of the night, while REM sleep dominates the second half. Your body prioritizes slow wave sleep early, when the restorative processes are most needed, and shifts toward REM sleep as morning approaches, preparing the brain to wake. This temporal organization means that cutting sleep short robs you primarily of REM, which is crucial for emotional regulation and creativity, while staying up late reduces deep sleep, which is essential for physical recovery. Your body temperature naturally drops in the evening, signaling it's time to rest. This decrease, triggered by the circadian system, helps initiate sleep by slowing metabolism and redirecting blood flow. As morning approaches, your temperature begins to rise again, gradually bringing you back toward wakefulness. This thermal rhythm is one of many signals your body uses to mark time, a gentle tide that ebbs and flows with the turning of the day. Melatonin, the sleep hormone, is released as darkness falls, nature's way of marking nighttime. Produced by the pineal gland in response to signals from the suprachiasmatic nucleus, melatonin floods your system as evening deepens, making you drowsy and preparing your body for sleep. It is an ancient molecule, found even in single-celled organisms, a chemical timekeeper that has been marking the boundary between day and night for billions of years. The Earth has experienced over 4.5 billion sunrises since it formed, each one unique, each one marking a single rotation of this ancient planet, and yet each one part of an unbroken chain stretching back to the earliest days when the sky was orange with volcanic haze and the moon loomed impossibly large overhead. Every sunrise you witness is part of that continuous sequence, a single bead on a string of billions, connecting you to the deep history of the world. Every sunset you witness is light from 8 minutes ago, arriving just in time. The photons that paint the evening sky in gold and crimson left the sun's surface before you stepped outside to watch, racing across the void to arrive at precisely this moment, to illuminate the atmosphere and scatter into the colors that have moved humans since we first looked up and wondered. Each sunset is a collaboration between past and present, between distant fusion and local atmosphere, a daily reminder that even the most immediate experiences are entangled with time. The cosmic microwave background is a relic of time itself, a glow from the universe's infancy. This faint radiation, detectable in every direction, is the oldest light we can observe, the afterglow of the Big Bang, and it carries within it information about the universe's earliest moments. To study it is to look back to a time before stars, before galaxies, before any of the structures we see today existed, a time when everything was hot, dense, and undifferentiated. It is the universe's baby picture, and it tells us where we came from. Time may flow differently in other universes if they exist. Some theories suggest that our universe is one of many, each with its own laws of physics, and in some of them, time might not exist at all, or might have multiple dimensions, or might flow backward. These ideas are speculative, beyond our ability to test directly, but they remind us that even our most fundamental assumptions about reality, that time flows forward, that it is one-dimensional, might be contingent, true only in this particular corner of a much vaster cosmos. The concept of eternity is not infinite time, but the absence of time altogether. Philosophers and theologians have long distinguished between everlasting duration, which is time without end, and eternity, which is outside of time entirely, a realm where past, present, and future are meaningless categories. It is a difficult concept to grasp from within the flow of time, but it points to the possibility that time itself is not ultimate, that there may be modes of existence for which temporal categories do not apply. Memory is how we preserve time, capturing moments that otherwise would vanish. Without memory, there would be no sense of continuity, no personal history, no identity stretching across years. Each recollection is a small rebellion against the flow of time, an attempt to hold on to what has passed, to make the ephemeral permanent. Yet memories are imperfect. They fade and distort. And this imperfection is itself a reminder that time always wins, that the past slips away no matter how tightly we try to hold it. Nostalgia is the mind's way of traveling backward through time. It is a bittersweet longing for moments that can never be relived, for places and people that have changed or vanished. Neuroscience shows that when we remember, we reactivate the same neural patterns that were active during the original experience, allowing us to briefly revisit the past, though always through the distorting lens of the present. Nostalgia reminds us that we are time-bound creatures, always moving forward, but forever looking back. Every decision creates a branching path through time that can never be retraced. Once a choice is made, other possibilities fade into what might have been, and you move forward along the path you have chosen, never able to return to that exact moment and choose differently. Life is a one-way journey through a landscape of forking paths, and the accumulation of choices, large and small, creates the unique trajectory that is your existence, unrepeatable and irreversible. This moment, right now, will never exist again, yet it is connected to every moment that came before. It emerged from the past and will give birth to the future, a single point in an infinite chain of causation, stretching back to the beginning of time and forward into the unknown. It is unique and fleeting, but it is also eternal in the sense that its effects will ripple forward forever, influencing everything that comes after in ways subtle and profound. Time flows onward, but in this quiet space, there is no hurry, no rush, only the eternal present of rest. The clocks may tick, the earth may turn, the universe may expand, but here, in this moment of stillness, time loses its urgency. There is only breath, only darkness, only the gentle drift towards sleep. And in this space, time becomes not an enemy to be fought, but a companion, a river that carries you softly into dreams. And so, our journey through the vast landscape of time draws gently to a close. We've wandered from the birth of the universe to the tick of an atomic clock, from the slow carving of canyons to the rapid spin of distant stars. We've touched the mystery of entropy and the quiet patience of ancient trees. Time, that invisible current, has carried us through billions of years, yet here we are, arriving softly in this single, peaceful moment. It can be humbling to realize that you exist at a precise point in an unimaginably long timeline. Every atom in your body has been on its own journey through time, forged in stars, scattered through space, assembled into this temporary form that is you. You are, in the most literal sense, made of time itself. And yet, for all its vastness and mystery, time has brought you here, to this quiet space, to this breath, to this rest. There is nowhere else you need to be. But for now, there is nothing more to do. Time will continue its patient flow with or without your attention. Let the mystery remain a mystery. Let the vastness remain vast. Just allow your body to sink deeper into rest, feeling the weight of the day dissolve like morning mist. Let time stretch out into something soft and shapeless. Let the tick of seconds fade into the silence. There is only this: warmth, stillness, darkness, and the gentle drift into sleep. If you've enjoyed it, you can gently like, subscribe, or leave a thought in the comments. It helps others find their way here too. Sleep well and let time carry you softly through the night. Good night.